In this lesson, we will focus on the fundamentals of hole machining, specifically drilling, reaming, and boring techniques, as well as the application of tools used in these processes. Explore the basic concepts of hole machining, the common methods of hole machining, and the types and characteristics of tools. We will also analyze the common issue of drill deviation. By studying these topics, you will gain a comprehensive and in-depth understanding of hole machining, laying a solid foundation for learning more complex machining techniques in the future. In the field of metal cutting, hole machining is a crucial technique widely used in various industries such as mechanical manufacturing, aerospace, and automotive. Next, let's delve into the fundamental knowledge of hole machining. First, we need to understand the basic concept of hole machining. Simply put, hole machining is the process of creating holes with specific dimensions, shapes, and precision requirements in metal materials. In actual production, holes are widely used, such as mounting holes on mechanical parts and oil holes in hydraulic systems. The quality of the holes directly affects the assembly performance and the operational performance of the parts, so ensuring the precision and quality of hole machining is crucial. Now, let's look at the common methods of hole machining. Drilling. Drilling is the most basic method of hole machining, where a drill bit is used to directly create a hole in the workpiece. The drill bit is typically a twist drill, which consists of a shank, a neck, and a working part. The shank is the clamping part of the drill bit, used to transmit torque and axial force. The neck is the connecting part between the shank and the working part. The working part is further divided into the cutting part and the guiding part. The cutting part is responsible for the main cutting task, while the guiding part serves to direct the drill bit and smooth the hole walls. During the drilling process, the rotational movement of the drill bit is the primary motion, while the linear movement along the axis is the feed motion. The precision of drilling is relatively low, with typical dimensional accuracy ranging from IT11 to IT13 and surface roughness RA between 12.5 to 50 micrometers. This is because the drill bit is prone to deviation during drilling, leading to skewed hole axis and enlarged hole diameters. Next is the issue of drill deviation. Drill deviation refers to the phenomenon where the axis of the drill bit shifts from the axis of the hole being machined during the drilling process. Deviation can severely affect the machining accuracy of the hole and may even result in the scrapping of the part. The main causes of drill deviation are as follows. 1. Geometric errors of the drill bit. If the two main cutting edges of the drill bit are asymmetrical, it can cause uneven force during cutting, leading to deviation. 2. Non-uniformity of the workpiece material. If the hardness of the workpiece material is uneven, the drill bit will encounter varying resistance during cutting, which can also easily cause deviation. 3. Run out of the machine tool spindle. Run out of the machine tool spindle can change the rotational center of the drill bit, thereby causing deviation. To reduce deviation, the following measures can be taken. 1. Pre-drilling a centering hole. Use a center drill to create a centering hole on the workpiece before drilling. This provides accurate positioning for the drill bit, reducing the likelihood of deviation. 2. Using a drill bushing. A drill bushing can guide the direction of the drill bit, improving the accuracy of the drilling. 3. Sharpening the drill bit. Ensure that the two main cutting edges of the drill bit are symmetrical, allowing for even force distribution during cutting. Here, we must emphasize the importance of craftsmanship. Drill deviation may seem like a minor issue, but it can have a critical impact on the overall quality of the part. This requires us to adopt a spirit of craftsmanship characterized by continuous improvement and meticulous attention to detail throughout the machining process, ensuring the quality of the work. Reaming is a method of enlarging an existing hole using a reamer. The structure of a reamer is similar to that of a twist drill, but it typically has more teeth, usually 3 to 4. The cutting edges of a reamer are distributed more evenly, making the cutting process relatively smooth. Therefore, The precision of reaming is higher than that of drilling, with dimensional accuracy reaching IT10 to IT12 and surface roughness RA ranging from 6.3 to 12.5 micrometers. Reaming can serve as the final machining of a hole or as preparation for fine machining processes such as honing. During reaming, because the cutting allowance is small, the cutting force is also relatively low. Therefore, a larger feed rate and cutting speed can be used to improve machining efficiency. Reaming is a method of fine machining a pre-drilled hole using a reamer. Reamers are divided into two types, hand reamers and machine reamers. Hand reamers have a longer working part and good guidance, making them suitable for manual reaming. Machine reamers, on the other hand, are used for reaming on machine tools. The precision of reaming is very high, with dimensional accuracy reaching IT7 to IT9 and surface roughness RA ranging from 0.8 to 3.2 micrometers. This is because reamers have many teeth, sharp cutting edges, and a calibration section, allowing for precise trimming and calibration of the hole. These are the methods for hole machining. Characteristics of hole machining tools. Different hole machining methods require different tools, each with its own characteristics. Drill bit. The cutting part of a drill bit has a complex shape and needs to have good cutting performance and rigidity. To enhance the cutting performance of drill bits, they are typically made from materials such as high-speed steel or carbide. Core drills. Core drills with evenly distributed cutting edges, allowing for smooth cutting and effectively improving the machining accuracy of the hole. Reamer. The calibration section of a reamer is relatively long, ensuring the dimensional accuracy and surface quality of the reamed hole. The cutting edges of a reamer are sharp, and the cutting allowance is small, resulting in lower cutting force and cutting heat during reaming. Consequently, the quality of the hole is relatively high. In the manufacturing process of automobile engines, a large number of holes need to be machined on the engine block, such as cylinder bores and bolt holes. The precision and the surface quality of these holes directly affect the performance and the reliability of the engine. When machining cylinder bores, the process typically begins with drilling a pilot hole, followed by reaming and honing for fine machining. This ensures that the dimensional accuracy and the surface roughness of the cylinder bores meets the required standards. In the aerospace field, there are also many high-precision holes in the structural components of aircraft. For example, the connection holes on airplane wings require extremely high precision. Advanced hole machining techniques and tools must be used to meet the safety and performance requirements of the aircraft. In the process of hole machining, controlling the precision of the hole is crucial. In addition to the previously mentioned measures to reduce deflection, precision can also be controlled by reasonably selecting cutting parameters. These cutting parameters include cutting speed (VC), feed rate (F), and depth of cut (AP). Cutting speed. Cutting speed refers to the linear velocity of a point on the cutting edge of the drill bit relative to the workpiece during the main motion. The formula for calculating it is VC equals pi times dW times N divided by 1000, where d is the diameter of the drill bit in millimeter, and N is the rotational speed of the drill bit in revolutions per minute. If the cutting speed is too high, it can lead to increased wear on the drill bit and reduce the precision of the hole. Conversely, if the cutting speed is too low, it can affect machining efficiency. Feed rate. The feed rate refers to the distance the drill bit moves actually per revolution, (mon, rev). If the feed rate is too large, it will increase the cutting force, which can easily cause drill deflection and increase the roughness of the hole wall. If the feed rate is too small, it will reduce machining efficiency. Depth of cut AP. The depth of cut refers to the vertical distance between the machined surface and the surface to be machined. When drilling, the depth of cut is equal to half the diameter of the drill bit. The size of the depth of cut directly affects the magnitude of the cutting force and cutting heat. it needs to be reasonably selected based on the workpiece material and the performance of the drill bit. In this lesson, we learned the fundamentals of hole machining, including drilling, reaming, and honing techniques, as well as the application of tools. We covered the basic concepts of hole machining, understanding that it is the process of creating holes with specific requirements in metal materials, and its quality is crucial to the performance of parts. The common methods of hole machining include drilling, reaming, and honing, each with its own characteristics and applicable scope. Drilling is prone to deflection, requiring appropriate measures to reduce it. Reaming can further improve the precision of the hole, while honing is a high-precision finishing method. We also studied the characteristics of hole machining tools and the methods for controlling precision in hole machining, including the reasonable selection of cutting parameters. Through practical application cases, we observed the importance of hole machining in fields such as automotive and aerospace. I hope that through this lesson, everyone has gained a deeper understanding of hole machining, laying a solid foundation for future learning and practice.